So, what if a piece of code could actually predict your risk of having a heart attack? It sounds like science fiction, right? Well, today we're diving deep into a machine learning system that's trying to do exactly that, exploring that fascinating space where code meets cardiology.
I mean, that's a huge question, isn't it? For decades, doctors have used their incredible experience and a handful of key signs to make these calls. We're going to break down how this system flips that script, analyzing hundreds of data points all at once, looking for those hidden patterns that could literally be the difference between life and death.
So, let's start with the why. Why is this such a tough nut to crack in the first place? Well, because predicting something like heart disease, it's not like following a simple recipe. It's truly one of the biggest challenges in modern medicine. Just think about everything a doctor has to juggle in their head. Your age, your cholesterol, your blood pressure, your family's medical history, your lifestyle. I mean, the list just goes on and on. For any one person, all these factors create this tangled web of data. Trying to find the single most important thread in that web, that is a monumental task. And this is exactly where technology, where an AI-powered approach can step in. Instead of a human trying to juggle all those variables at once, this project puts forward an AI system that's built from the ground up to handle this exact kind of complex data problem. So what are we really talking about here? At its core, it's a predictive tool. It's pretty straightforward. You feed it a person's medical data, and it uses a specially trained AI model to basically calculate the odds that heart disease might be present. Okay, and this is where it gets really interesting. That number 8. You see, this system isn't just betting on one horse. Nope. It actually sets up a full-blown competition, pitting 8 different machine learning models against each other to see which one comes out on top as the most accurate predictor. All right, so let's pop the hood and see what's actually making this thing run. To really get it, we need to understand 2 key parts. First, the data it's learning from, and second, the algorithms, or as we're going to call them, the contestants in this competition. You know, every AI needs its homework, its textbook to study from. For this system, that textbook is a real-world, anonymized medical data set from 303 different patients. For each person, the AI scrutinizes 14 different health metrics, things you'd expect, like cholesterol and max heart rate, to learn what kinds of patterns are linked with heart disease. And here they are, the contestants. Each one of these algorithms has a totally different game plan. You've got logistic regression. That's kind of like the old school statistician, just calculating the simple odds. Then there's the decision tree, which is more like a detective asking a chain of if this then that questions. And random forest? That's not one detective, it's a whole committee of them, and they all vote on the final answer. It is a true battle of the bots.
Okay, so you've got this algorithmic showdown, right? 8 different models all vying for the top spot. How in the world does the system pick a winner? Well, it's definitely not random. It's a super rigorous, automated competition designed to find the absolute most reliable algorithm for the specific job. And the game plan is actually pretty straightforward. First, you split the data into a training group and a testing group. Then, you train all 8 models on that same training data. After that, you test them on data they've never seen before and score how well they do. And finally, the model with the highest score is crowned the champion. Simple as that. Now that first step, splitting the data, is absolutely crucial. The system uses a clever technique called stratified sampling. Look, in simple terms, all it's doing is making sure the practice test is in a cakewalk while the final exam is impossible. It guarantees that both the training and testing groups have the exact same mix of patients with and without heart disease, which prevents any kind of unfair or biased result. So how do you judge these models? Well, there are 2 big criteria. First is accuracy. That's easy enough. How many times did the model get it right? But, and this is so important in medicine, you also have the F1 score. This one asks a much more critical question. Is the model good at avoiding false alarms while also not missing actual cases? You have to get that balance right, because a misdiagnosis is obviously way more serious than a false positive. And once the dust settles from that competition, the system doesn't just hand out a trophy. It automatically saves the winning model, all of its settings, everything about it. This champion model then becomes the permanent brain, the engine that's going to power the actual prediction app that a person can use. Okay, but all this behind-the-scenes competition and training, it doesn't mean a thing if a real person can't actually use it, right? So now we get to the final, and maybe most important stage, turning all that sophisticated code into a simple, useful tool.
And here's what you'd actually see. This is the front end. No messy code, just a clean, simple form. A user, maybe a researcher or a medical student, would just type in the key health numbers for a patient profile right into these fields.
And after you hit predict, all of that incredibly complex math and modeling just boils down to this, a beautifully simple result. The output is binary. A 0 means the model sees a low probability of disease, while a 1 flags a high probability. It's a crystal clear answer from a very, very complex process. So what's the big picture here? What's the real purpose behind all of this? Because it's about more than just getting a 0 or a 1. The real goal here is to build a bridge. It's designed to take the abstract, kind of intimidating world of machine learning algorithms and make it tangible, make it accessible, especially for people in healthcare, in research, and in education who want to start exploring the potential of these amazing technologies.
And look, this next part is maybe the single most important takeaway from this whole thing, so it's worth saying very clearly. This is a powerful tool, for sure, but it's for learning and for research. It is not a doctor. Every single medical decision, without exception, must be made by a qualified healthcare professional.
And that really leaves us with a big, open question, doesn't it? As these AI tools get smarter and smarter, as they get better at seeing patterns that we humans might miss, the real challenge ahead is figuring out that partnership. How do we perfectly blend the raw analytical power of AI with the wisdom, the intuition, and the empathy of a human doctor? That's the huge conversation a project like this helps us all begin.